Now we will start with rotation matrices. Let's start by looking at frames. A frame is completely represented by its axis. It is the same to say frame or to say coordinate system. Here we have an example. Let's see frame A. Frame A is defined by the axis XA, YA, and ZA. The hat here represents a unit vector. If we want to represent this XA in frame A, this will just be 1, 0, 0, which is X. This superindex here represents the reference frame. It is with respect to. So this is X sub A with respect to A. If we want to represent Y sub A in the frame A, it will be 0, 1, 0. And for Z sub A in frame A, it will be 0, 0, 1. Now let's see frame B. Frame B has a rotation with respect to the previous frame. In this case, if we want to represent XB in its own reference frame, that is in frame B, it will be again just 1, 0, 0. YB in reference frame B will also be 0, 1, 0, and ZB will also be 0, 0, 1. Now, what rotation matrices do is they represent this axis in terms not of the same frame, but in terms of another frame. For example, this axis of B in terms of A or vice versa. So the generic rotation matrix can be derived as follows. Let's consider two frames, A and B, the blue one and the red one. They have a common origin, as you can see here, but they are rotated one with respect to the other. The objective is to describe frame B, the red one, with respect to frame A, the blue one. We just saw that a frame is completely described by its axis. So if we are able to describe the axis of B in terms of A, we are done. So we want this XB in the frame A, YB in frame A, and ZB in frame A. The coordinates of the axis of B with respect to A will be given by the following expression, which can be obtained using projections. Now, how do we obtain this expression? We have this XB. The component of XB in terms of XA is just the dot product between XB and XA in the direction of XA, and that's this one, XB dot product XA in the direction of XA. For this part, it's the dot product between XB, YA in the direction of YA, XB, YA in the direction of YA, and for ZA, it will be XB dot ZA, this with this ZA in the direction of ZA. We do exactly the same things for the other axis, for Y and for Z. Now we can represent this in a vector form. For example, for this first element, this would be the first component, the second component, and the third component. That's this one, the first, second, and third. And we do the same for all the other elements, for Y and for Z. Now we want to find one matrix R, so that the axis of B with respect to A follow this following convention. We want X of B in frame B to be multiplied by this R and to get the same vector but now in frame A. We want the same for Y. If Y is in frame B, we want to multiply with R and obtain the same Y but now in frame A. And we want the same for Z. The matrix that will satisfy this is this one. You can easily check it, because if you multiply it, for example, with this X, XB in B, if you recall from the previous slides, it is 1, 0, 0. So it would be 1, 0, 0. If we multiply that, we just get this 1 and here 0 and 0. So we just get XB in terms of XA, in terms of frame A, which is what we wanted. This is called a generic rotation matrix. So the rotation matrix of frame B with respect to frame A is represented as this, B with respect to A. And here we have XB with respect to A, YB with respect to A, and ZB with respect to A. Here I'm just replacing the components. This is a very important definition, and it says that every column represents the axis XYZ of frame B, because it's B here, with respect to frame A, because A is the reference frame. We have frame B with respect to frame A, B with respect to A, which is the matrix that we just saw. Here the first column is XB in terms of A, YB in terms of A, and ZB in terms of A. Now if we want the opposite, if we want frame A with respect to frame B, we do the same thing, the same idea. So now it would be XA in terms of B, YA in terms of B, and ZA in terms of B. And this matrix would be denoted as RA with respect to frame B. Now you can see that these two matrices have something in common. If we rewrite this matrix, we see that here the row is exactly the same as this column. This second row is also the same as this second column. And this third row is the same as this third column. So we can say that this matrix is a transpose of this matrix, and that is a very important definition. That RA with respect to B is the same as RB with respect to A transposed. Let's see a first example. We have the following frames, A and B, and we want to obtain the rotation of frame B with respect to frame A. To obtain the rotation of frame B with respect to frame A, we have to represent each of the axes of frame B in terms of A. So the result will be this one. Let's go term by term. This first column is XB in terms of A. So this XB, the dot product of this XB in terms of this XA would be just cosine of 90, because these are unit vectors. So I just care about the cosine of 90 here. Then XB in YA, there's no angle here, so it is 0, cosine of 0. XB with ZA, the angle is 90, so this is cosine of 90. Now for YB and XA, the angle is here 180. YB and YA, the angle is 90 here. And YB and ZA, the angle is again 90. And we do the same for ZB. Now we want to obtain the rotation of frame A with respect to frame B. We can do it again following the same idea. So now we have XA in terms of XB, which is just cosine of 90 degrees, this term. Then XA in terms of YB, which is, here we have 180 degrees, so cosine of 180. Then XA in ZB, again cosine of 90, and we continue like that. We can see easily that one is a transpose of the other. In the second example, we want to obtain the rotation of frame B with respect to A. This is a rotation about the Z-axis. So we want to describe this XB in terms of XA. You see that this XB has an angle of theta with respect to XA. So it would be cosine of theta. Then this second element would be XB with YA. The angle here is 90 minus theta, as you can see here. And the third one is this XB with ZA, and the angle is 90 degrees, so we have the cosine of 90. We do the same for YB and for ZB, and if we simplify this, we get this representation. This is a generic rotation about Z-axis. We can obtain similarly the rotations about X or about Y. As an example now, let's consider this rotation, and we have to plot frames A and frames B. So this is RB with respect to A. We know that this is the basis, XA, YA, ZA. The columns represent the axis of B in terms of A. So this first column is XB in terms of A. So XB in terms of A is 0, 0, 1. It means that it is Z. It is this one. So this will be XB. Now the second column is YB in terms of A, and it is minus 1, 0, 0. It means that it is in the direction of minus X. So it will be in minus X, just here. The third one is ZB in terms of A, and it's 0, minus 1, 0. It means that it's minus Y, so it is in this direction. As a fourth example, we have some frames, and we want to find the rotation that relates frame 2 to frame 3. So we want this 2 in this frame 3. What we do is we can do this by inspection. X2 is just Y3, so X2 is Y, 0, 1, 0. Y2 is X3, so it will be 1, 0, 1. Now Z2 is minus Z3, so it will be 0, 0, minus 1. Some elementary rotations are the following. This is about the X-axis, this is about the Y-axis, and this is about the Z-axis. We have in one example derived this expression. We can do the same for both of these expressions as well. These three matrices are very useful when dealing with rotations.